Hello and welcome to the final part of the logarithm series, where we're going to go over some unique cases of solving logarithms. Now, when we're solving special cases of logarithms for values that aren't as nice, for instance, an exponential that gives you 2.5 raised to the x power equals 8. We already know that there is no x value that is an integer like 1 or 2 or 3 or 4 that is going to give us 8 from 2.5. So we need to use a logarithm to help us solve this. So if we take the log of both sides, then what we end up with is a nice little logarithmic equation where we can start using some of our properties from the previous video. Well, wait a minute here. That x value we can drop off to the front, and we get x log 2.5 equals log 8. Well, let's see. This is a constant our calculator can calculate for us. This is a constant our calculator can calculate. So essentially, x is going to equal log 8 over log 2.5. This you would do strictly in your calculator, or your instructor may want you to leave it just like this. Depends on your teacher. Now, there is a unique problem where if you don't have a calculator to help you fix a logarithm, you can use what's called the change of base formula. And the change of base formula is very useful, especially if I give you like log of 2.5 or 2.88, I'm sorry, not 2.5. And, we want to punch this into our calculators. Well, then we can just use this formula accordingly. Let's test this theory. So if I give you log 416, well, that should equal 2. Let's take out that 2 and replace it with our change of base. Now, if you punch this into your calculator as log parentheses 16 close parentheses divided by log of 4 parentheses, of course, that should equal 2. And you can use your calculator to verify this. So why does this formula work? Well, there are multitudes of reasons that we can go into, but that just takes a longer proof than what most of you are expecting at the moment. So let's take a nice little logarithmic property that involves when you have two logs on either side of the equation. Well, wait a minute. Hold on a second here. We streamlined straight through this. Log of 7x equals log of 7/2, therefore x equals 2. Well, for a visual appeal, yes, these two items have to be equal to each other. But there is a property that we can use to help us establish how to simplify this expression. If both these bases are the same, then you can raise both of the original parts to their base. Aha! So this property is known as the base replacement, as some people would put it. Whoops, let's keep up for consistency here, folks. So if I give you a base raised to a log of the same base, a, then the output is going to be a. This is a unique item that comes in handy if and only if you have a log on one side with a log on the other and you want to cancel out the log altogether. Otherwise, you would just use your normal conversion that says b to the y power equals x, right? Remember video number 1? Still with me? Awesome. So let's see how the rest of this math works out. Well, using that base replacement formula, the bases completely cancel each other out, and now you're left with x equals 2. Nothing simple? Actually, it is rather simple, and it works really well if the bases are the same. So keep that in mind. I know there's a lot of repetition here, but this is a special cases video. In other words, we want to go over specific cases, such as change of base, or when we have the base replacement, or if you just need to solve a logarithm altogether. But again, these are the two dominant cases within this video. We're not going to keep this too long, but now you have all the components needed to start solving logarithmic equations. Use them to your advantage and you will have fun with logarithms. This is the Tall Guy, signing out.